Hi guys, how are you? Welcome to week 12, and this should be our last lecture. I might break it up into two pieces. We'll see how it all goes, but just to let you know there for next week, I won't leave you hanging. I'll post some questions and answers and this kind of thing, possibly some type of exam review. But I hope you guys are doing awesome. I hope you guys are well and that you guys are safe. It's Friday night here. If you hear some snoring, it's my beagle over on the sofa. The family's all gone to sleep. So, hi, this is Ian. Let's get this going here. Welcome to basically the conclusion of the introduction there for chemistry. As I said, we'll see if we can get through this in one shot, but we may break it up into two pieces there, and I might post another video there tomorrow. A lot of this, the first half is going to be review. And what I've done there is, let's just go on here. This is stoichiometry. This is where we're going. The past couple weeks there, we've been dealing with the mole itself and using those two triangle formulas. Okay. The whole point of learning those is for this thing called molar stoichiometry, which we're going to get into there today. Accurate measurements and calculations of the correct dosages are important in dispensing the correct medicine. Now, this is all involved in chemical reactions, and starting with reactants. And if I have 5 grams of this reactant and 8 grams of this reactant, what predictions can I make about how much product I'm going to make? And we'll get there towards the probably about halfway through the PowerPoint here. What I've done, if you've had a look at the PowerPoint there before I posted this video, is the questions there, because I don't have access to a proper whiteboard setting that I'm able to videotape and show you guys all this. What I've done here is I've put you have the question there from the PowerPoint, which I would normally do on the whiteboard, but I provided the answer and how I would do it, and how in mathematics there's 3 or 4 different ways to answer a question. And what we've got here now is what I think is the best way to do it. When you do the review questions there that I posted at the end of the PowerPoint, of which you have answers to from the textbook, you'll notice there that they will do the questions, they will answer them differently. And some people know that way there from high school. It's called the factor label method. There's this way here, so you have two ways available to you. This slide here, what is the molar mass of aluminum chlorate? We've been doing this there for the past couple weeks, and there's 1 aluminum, there's 3 chlorines, there's 9 oxygens, and you just multiply by their molar mass, which you find on the periodic table, which was the same number there as the atomic mass. Okay, but now 1 mole of aluminum weighs 26.98 grams. Okay, 1 mole of chlorine weighs 35.45, but because there's 3 of them, I multiply by 3. I have 9 oxygens times its molar mass, which is 16. You add them all up, you get 277. And you will notice that my numbers here could, and you see how it varies from this number here, statistically they're the same. And on a multiple choice test, which is what your final exam is going to be, okay, there's going to be 4 different answers. And I would never, if the answer is 277.333, I wouldn't give you 2 answers that are almost identical. Okay, there's going to be 1 clear answer. So if you've done the math, you're going to use a different periodic table Okay, the one that you use is different from the one that I use. Mine goes to like 4 decimal places, but it's not a big deal. If you do the math correctly, there's only going to be one answer. Calculate the mass of 2.5 moles of aluminum chlorate. Well, now, and part of this video is going to be training you how to do this exam, because you know what questions are going to come. Every question we've done there, you know, since week 8, but you never know which one is going to come next. It's going to be mashed potatoes. All right, so you have to handle every single question the same way. You have to kind of regroup and start fresh. What is he asking me? Well, in this question here, he's asking, calculate the mass. So he's looking for grams. Ding, ding, ding. What formula do I know that has grams in it? Well, there's only one. Grams is equal to moles times molar mass. Okay, that's one of the triangles. What information did I give you? Well, I gave you moles. Does that work? Aha. Grams is equal to moles times molar mass. I give you the moles. You always have the molar mass. Where do you find that? Okay, that's from the periodic table. And this is just a transfiguration there of the triangle formula there. One of the 2 triangle formulas I gave you. Plug and play. 2.5 moles times 277.5 grams per mole from the previous slide gives you 693.33. And you see how this number here is a little different, but logically there's only going to be one answer that you will be able to choose. Okay? Calculate the number of moles in 3.52 grams of aluminum chlorate. Well, what am I asking for? Number of moles. What formula do I have? Well, I have 2 formulas that have moles in them, right? Both triangles have moles in them, so that doesn't give me enough information. 3.52 grams is what I gave you. So logically, you're going to use the one triangle formula that has moles and grams in it. Moles is equal to grams divided by molar mass is equal to 3.52 grams. Again, the molar mass of aluminum chlorate, we found it there from a couple slides there before. There we go. Now, 0.01268 moles. There's way too many significant figures here because I only give you 3 significant figures here. So you're only limited to 3 significant figures. And so 1268 would be 127. Being able to change this into scientific notation, this number here is less than 1, so the exponent here on the scientific notation should be negative. Okay? Molar conversions, mass to molecules. So what we're talking about here, grams, which is one formula, triangle formula, to the number of molecules, which is another triangle. So look at this one here. Calculate the number of formula units. So calculate the number of molecules contained in 12.4 grams of aluminum chlorate. So what am I looking for? I'm looking for the number of formula units, or the number of molecules. Well, this is aluminum chlorate isn't a covalent compound, it's an ionic compound. That's why we call it formula units. So I'm looking for the number of molecules, which is what formula? What's the only formula that has the number of atoms, number of molecules, number of formula units at the top? Okay. What information did I give you? I gave you grams. So I'm actually giving you information from one triangle, and you're going to have to use that information to find out information using the other triangle. And if you go back to last week's PowerPoint there, you'll see a slide there where the 2 triangles are side by side, but there's a bridge between them. Okay? And the bridge is moles. So if you get a question like this where I give you information from one triangle, but I'm asking for information from the other, the key is to find the moles and then substitute it into the other formula. Okay? So the plan is here, going from grams to the number of units. Find the moles, then sub into the other triangle, other formula. So I'm going to look for moles. Moles is equal to grams divided by molar mass. I gave you grams. So 12.4 grams divided by 270.5. Here I found the number of moles. You substitute this into your other formula. And we are looking for the number of atoms or molecules or formula units, which is the top of the other triangle, which is equal to moles times Avogadro's number. And there we go, 2.69 times 10 to the 22. Pause this video at any time, try this out. That's an exam question. I'm only going to change the numbers. Okay? You know it's coming. There you go. What is the mass of 3.6 moles of calcium chloride? All right. So what is the mass? I'm asking for mass. I give you moles. You would use this formula here. Find your answer. Okay. And again here, 400.71. You would round up 401 grams. How many moles of hydrochloric acid are contained in 18.2 grams of the compound? Again, reset. What am I asking for? Moles. What information did I give you? Grams. There you go. Plug and play. Okay? What is the mass of 1.6 times 10 to the 23 molecules of hydrochloric acid? So what am I asking you for? Grams. What information did I give you? Molecules. So this is one of those guys where you're going to have to take information from one formula, jump it over to the next. So the plan is going from number of molecules to grams. We have to find the bridge. We got to find the number of moles. So the number of moles is equal to the number of molecules divided by Avogadro's number. You don't have to memorize any of this stuff. You will have your formulas by your side. Okay? You substitute in what I gave you, 1.6 times 10 to the 23 divided by Avogadro's number. There's your number of moles. Plug that into your next formula. Okay? You have your molar mass always. And there you go, 9.69 grams. What is the percent carbon in ethanoic acid, which is acetic acid, which is vinegar? So what is the percent of carbon in this guy here? How do I do percent? First, you have to find the molar mass of the whole thing. So you have 3 carbons times 12. 6 hydrogens times 1, these are your molar masses here. 2 oxygens times 16, so the molar mass, okay, oh, this is not ethanoic acid, this is propanoic acid. Thought that looked funny. I'm going to change that right now. Thought that looked funny. Propanoic. So, propanoic acid. The molar mass of propanoic acid is 74 grams per mole. What are we looking for? We're only looking for carbon. So, how many carbons do I have in propanoic acid? I have 1, 2, 3. So, percent composition is equal to the atoms and the type divided by the molar mass, which is 3 carbons divided by the molar mass, which is 36 grams, divided by 74 grams, because you found that out already, which is equal to 48.6%. Not so bad. Try a couple of these and they tend to become a little routine. Percent yield. Percent yield just means you have your actual, what you actually made in the laboratory, as opposed to how much you should have made. And what I mean by that is, if a perfect being was mixing A and B, and they were able to count atoms, and you know how sometimes solutions get stuck to the side of the test tube and all this, and yeah, you lose some here and there, but generally, we're imperfect beings, and that's just the way it is. You're not going to have a Walter White Breaking Bad 94%. It's unheard of. So what this means is your percentage yield is how much did you make in the laboratory divided by how much you could have made, like 100%. All right, and then you multiply this whole thing by 100%. And if you look at the example here, if it is expected to make 95 grams of a product, if it is expected to make 95 grams of a product, so that's your 100%. Okay, if a perfect being was doing this experiment, they would have made 95 grams of it. And after the experiment, you realize you only made 65 grams. What is your percentage yield? Well, plug and play. Okay, 65 grams divided by 95 grams, which is your actual, divided by your theoretical, multiplied by 100, 68.4. So your percentage yield was only 68.4%. Okay? Now we get into this molar stoichiometry. Okay, and it's kind of based on, I'm just going back a slide here, it's kind of based on this whole theoretical, how much you could make. And for the past, I don't know, since week 8, I've been kind of prepping you for this moment already. And some of this is going to seem awfully familiar. All right. Stoichiometry expresses the quantitative relationship between reactants and products. So if I have X grams and this are 5 moles and 6 moles, how much in theory can I make of my products? Stoichiometric coefficients and a balanced equation indicate molar ratios. You've already seen molar ratios. Stoichiometry allows us to predict certain values, how much reactant is needed, how much product can be made, and we can compare how much product we made experimentally to what we could have made theoretically. And there's your percentage yield. And this all comes from Khan Academy. So the stoichiometry, we'll start you off here and just have a look. So stoichiometry deals with the quantitative relationship between reactants and products. So you have a look here. Here I have 1 mole of nitrogen gas plus 3 moles of iodine produce 2 moles of nitrogen triiodide. Now, the most important thing you can do when you're dealing with, here we're going to start counting how much of this and how much can we make here. If I made this much, how much did I need over here? The most important thing you can do, and I've already been prepping you for this, your assignment number 2 was all over this. First thing you do is you make sure that it's balanced, and in this case here it is. I got 2 nitrogens here, 2 nitrogens here, I got 6 iodines here, I have 6 iodines here. Okay? In an exam question, I'll tell you if it's unbalanced or I'll tell you if it's balanced. All right? But the most important thing you need to do is you calculate your molar ratio, which you guys already did. You did it 100 times in assignment 2. And the only reason I was doing it was to prep you for this. Your molar ratio is 1, 3, and 2. All right? Because in theory, 1 mole of this and 3 moles of this will produce 2 moles of this. That's your theoretical. All right? A good little question here. Our molar ratio is 132. But is 262 wrong? Like if I multiply this guy by 2, multiply this guy by 2, multiply this guy by 2. Okay? Oh. Sorry, that should be 4. Late at night doing this stuff. But is 264 wrong? No. We always like to have the smallest though. So when you're doing these balancing equations, which you guys did very well on, and I was very impressed on the assignment 2, it's all about getting the smallest numbers there. All right, let's have a look. So calculate the number of moles of this guy here that can be made from 2 moles of nitrogen. So we want to know how much of this I can make if I give you 2 moles of this. Well, we already know, because on the top of every one of these in a testing situation, the first thing you're going to do is you're going to write a 1, a 3, and a 2. That's going to be up here, just like in my example. All right? Bang, bang, bang. It's right there. That's your theoretical. Okay? That's what's going to guide you. Now, what am I looking for? Calculate the number of moles of this guy here. So I'm going to put an X here. And what information did I give you? Well, I'm going to give you 2 moles of this. So, stoichiometry is all about boxes. You're going to make boxes. Now, here I've got 1 mole of this guy can make 2 moles of this guy. Well, what if I give you 2 moles of this guy? And you see, I just do a box. 1 to 2, 1 to 2 is 2 to x. 2 to x. And then you just cross multiply and you find x is equal to 4. Now let's go back. Does that make sense? If 1 mole of this guy can make 2 moles of this guy, well, if I double this, then 1 to 2 is equal to 2 to 4. That's all this stoichiometry is. It's just boxes. It's just doing these. Let's try another one. Calculate the number of moles of I2 required to completely react with 2 moles of nitrogen. So again, here I've given you the exact same chemical equation. What are you going to do? 1, 3, 2. All right. What information am I looking for? Calculate the number of moles of iodine. So X required to completely react with 2 moles of nitrogen. We'll put it 2. And look, I circle my boxes. I circle my numbers. I create my box. X is equal to 6. Now, does that make sense? 1 mole of nitrogen, I need 3 moles of iodine. Well, if I have 2 moles of this, then I'm going to need 6. Okay? Now, these guys here, they've been whole numbers, and it's kind of actually visually not so bad to see. Some of them, not so easy to tell. Okay? Just do your boxes. You'll always get the right answer. So here we have calculate the number of moles Okay, nitrogen triiodide that can be made from 5.5 moles of nitrogen. So again, there's your equation. It's the same equation as before for simplicity purposes, but you're going to get an equation. You're going to write your molar ratio, 1, 3, 2. What am I asking for? Calculate the number of moles of nitrogen triiodide. Well, I'm going to put an X. See, it's all right here. I write it all out. So there's an X moles. What information did I give you? 5.5 moles of nitrogen. So you see here, I circle what's going to be my box. And you see the variations here? You could get boxes here. You could get boxes here. You can even get boxes all over the place, as long as you set it all up. So here I have 1 mole can make 2 moles. Well, 5.5 moles can make, cross it up, 11 moles. Mole, 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 mole. And that's why we've got molar conversions, mole, mole, because we'll show you something in a little bit. Calculate the number of moles of iodine needed to react with 5.5 moles of nitrogen. And again, you do your molar ratio. Where's your X? Where's the information I give you? Cross it up, away you go. And again, pause the video, try these out for yourself. Here's another one. How many moles of aluminum are needed to make 0.0935 moles of hydrogen? Well, I don't know. But here's the balanced chemical equation. There's my molar ratio, 2, 6, 2, 3. You have to do that every time. That's the only way I can do it. Okay? And now what information am I asking for? How many moles of aluminum? So then what I do is put an X under aluminum. Okay? What information did I give you? 0.0935 moles of hydrogen. Well, hydrogen's all the way over there. Doesn't matter. Circle what my box is going to be. Crisscross, away you go. That's all these are. Mole are the easiest. Your molar ratio, these guys here are in moles. Woo. Okay? These guys here are in moles. Okay? If I'm asking for moles and I give you moles, they just go under here and it's one box. Easy peasy. Okay? This is just the same question. You can have a look at it. All right? It's a molar conversion, moles to moles. It's just the same question, just changing the numbers around. Which of these statements is not true about the reaction? 1 mole of nitrogen is needed for every 3 moles of iodine. 1 mole of nitrogen is equal to 3 moles of iodine. Well, that is true. 3 moles of iodine can produce 2 moles of nitrogen triiodide. 3 moles of iodine can make 2 moles of this. Good. 1 gram of nitrogen is needed for every 3 grams of iodine. That is incorrect. Now, let's go back to this. Your molar ratio is 1, 3, 2. That is moles. 1 mole of this can make 2 moles of this. 3 moles of this can make 2 moles of this. 1 mole of this plus 3 moles of this can make 2 moles of this. It's all about the number of moles, not grams. That's why we have our formula, triangle formula. We calculate stoichiometry in moles, but we measure in the lab with grams. And 1 gram of nitrogen is not equal to 1 gram of iodine. You can't compare them. All right? We can compare moles, but not grams. How many moles of hydrogen fluoride will be produced by the complete reaction of 1.42 moles of hydrogen in the following equation? So how many moles of HF will be produced by the complete reaction of 1.42 moles of this? Again, your molar ratio, 1, 1, 2. Where's my X? Go over here. What information did I give you? 1.42 over here, just like it's been set up crisscross. Okay? This is mole, mole. Again, this is mole, mole. I give you moles. I'm asking for moles. One box, away you go. Same thing. Now we're getting into, though, I'm not just going to give you moles. You see these ones here we saw there before. If I give you moles and I'm asking for moles, it's easy peasy. It's one step, bang, bang. But what if I gave you grams instead of moles? What would you do with grams? What formula do you know that you can change grams to moles? So if I give you grams, you gotta flip it to moles, and then you do your mole, which is what we've just been doing. I could give you molecules, number of atoms. What could you do? You have to flip it to moles, and then you go and do your mole. All right, which you're gonna get moles. Your answer is gonna be moles, but then I could ask for the answer in grams, or I could ask for the answer in the number of molecules. So you see here, this is what we've been doing there the past 5 or 6 or 10 slides. Is this right here, mole to mole, easy peasy. But if I gave you grams, you got to flip it. If I'm asking for molecules, you do this, but then at the end, you got to flip it. You have to do that extra triangle formula. Okay? Let's try one out, shall we? How many moles of propane are consumed when 1.81 times 10 to the 23 molecules of CO2 are produced in the following equation? You're thinking, okay, what? So here is your balanced chemical formula. All right. Propane plus 5 oxygen, 3 carbon dioxide, and 4 moles of hydrogen. And I mean that. First thing you got to do for all of these, molar ratio. 1, 5, 3, and 4. You do that for every single one of these. Just like down in here. There you go. Now, what information am I asking for? How many moles of propane? X moles. Same as before. What information did I give you? 1.81 times 10 to the 23 molecules of CO2. Wait a second. 1.81 times 10 to the 23 molecules? Well, this is in moles. This is in moles. This is, I'm asking for it in moles. This one here is in molecules. It's not going to wash. You have to change this to moles. So I give you molecules. What formula do you know that has molecules to moles? Okay, you know what triangle formula that is. And first we must convert to moles. Okay, with moles is equal to the number of atoms or molecules divided by Avogadro's number. You do your calculation, you get an answer of 0.300. Substitute that back in over here. Now you can do your box, and it's right back to where we were. Okay. All right, let's have a look. Problem solving strategies for stoichiometry. Okay, you have to convert. If I give you grams or if I give you number of molecules, bang, you got to convert to moles. No do to boot it. Convert the number of moles of starting substance to the moles of desired substance. That's mole. That's what we were doing. And then you may have to switch back into grams or the number of molecules. Let's have a look here. What mass of hydrogen, which has a molar mass of 2.02 grams per mole, is made by the reaction of 3.0 moles of hydrochloric acid with excess aluminum? So here's our chemical formula. We write it out. There's our molar ratios already done. What information am I asking for? What mass of hydrogen? So, and in this case here, I put X grams because this is all in moles, but I'm looking for X grams. What information did I give you? By the reaction of 3.0 moles of hydrochloric acid. So 3.0 moles of hydrochloric acid right here. But I also give you a little bit extra information here. Here I have excess aluminum, which means I have too much. All right? I have so much of this that it's just going to keep reacting with this and reacting with this and reacting with this, and then eventually this is just going to go away. It's going to run out, and I'm going to have this left over. So when you see excess, okay, what we're talking about here is that this one is going to go to 0, and the reaction is going to shut. So recap. Here I got my molar ratios, moles, okay. I gave you moles. I gave you excess here, which is just too much. But whenever you see excess, this one here is just going to go to 0, okay. And I'm looking for grams. All right. And going back into here, this one here I have too much. This one here I'm going to run out of. There's a word, a term that we call this one. The reactant that we run out of, we call that the limiting reactant or limiting reagent, okay, which we'll get into more. But you see here, mole, 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 gram. I'm asking for grams. Well, I got mole, mole, mole. I can do a box. And that is going to give me an answer of 1.5 moles. So I do my box, 6 to 3, 3 to X. I get an answer of 1.5 moles. But that's not what the question is asking for. I'm asking for grams. So you have to take this 1.5 grams of hydrogen and convert it using your triangle formula. And you get an answer of 3 grams. Okay. Here, molar stoichiometry, mass to moles. Okay, same formula or same chemical reaction that's going on here, and it's a different question. How many moles of hydrochloric acid are needed to completely consume 2 grams of aluminum? So, molar ratio, plug in what you know. What am I asking for? How many moles of hydrochloric acid? X moles. Okay, what information did I give you? I gave you 2 grams. Whenever you see grams or that kind of thing in this situation, should be a red flag. Because I can't compare grams and moles. I gotta get this into moles. 2 grams of aluminum, the number of moles is equal to grams divided by molar mass of aluminum, which is equal to 2 grams divided by 26.98, which is equal to 0.074 moles. Now, I know, you plug that in. And now here's your box. Okay, here's your box. And you get this answer here. 2.2 times 10 to the negative 1. All right. Again, same thing. Now, I can either give you grams, ask for moles. I could give you moles, ask for grams. But have a look at this one here. It's the same thing. What mass of aluminum nitrate? And here I gave you the molar mass. I may ask you to find the molar mass, but you can find the molar mass of that in 5 seconds. No, 20 seconds. Okay. What mass of aluminum nitrate is needed to react with 0.093 moles of sodium carbonate? So here I'm asking for the mass. I give you the moles. So write it out. There's your molar ratio. I'm asking for grams. I give you moles. Okay, mole, mole, mole. You can do a box, which will give you moles. But now the question is asking you to convert that into grams, and you just use your formula and away you go. Same question, just changing the numbers around. It's actually even the same formula. Okay, so try these out, and yeah, do them a couple times, it'll click. How many moles of oxygen are consumed when 38 grams of aluminum oxide are produced in the following equation? Again, same thing. I'm looking for the number of moles, give you grams. Now I could give you grams, I could give you the number of molecules. Doesn't matter, you could use either of the triangle formulas to find moles, which is what you would do to plug in here. Yeah, there we go. Right here, what mass of hydrochloric acid is produced when 1.81 times 10 to the 24 molecules of H2 react completely in the following equation? So here now, look at this one. What mass of hydrochloric acid is produced? So I'm looking for grams, but I give you molecules. So let's have a look at what we've done here. There's our chemical equation. We did our molar ratio. Plug in what I'm asking for. I'm asking for X grams of this guy. So I'm looking for grams here. When you see that I'm asking for grams, there's an extra step I'm giving you. I've given you molecules. Well, this is in mole, this is in mole. Molecules don't work here and grams don't work here. So in order to figure out what X is going to be, I have to flip this to moles. Okay? So you find your number of moles here. Okay? So here is your box. There's your box. Solve for X. And then once you get, so the answer here is going to be 6 moles. But that's not what they're asking for. They're asking for grams. So then you change X moles into grams. Grams is equal to moles times molar mass. Moles is 6 moles. The molar mass of hydrochloric acid is 36.5, which is equal to 219 grams. Okay? And that's basically what this is. These are the toughest of them all. Okay? When I give you mass to mass or molecules to mass. Because you see here, let's go back to this previous one here. This is all in moles, but I gave you something that wasn't moles, and I'm asking for something that isn't in moles. So there's an extra step before I even start, and there's an extra step at the end before you get the final answer. And that's what this one is here, mass to mass. This is the toughest of them all. All right. What mass of bromine is needed to completely consume 7 grams of aluminum? So I'm looking for grams of bromine. So right then and there, there's an extra step at the end. I give you grams of aluminum. There's an extra step right there at the start. You got to flip that to moles. Okay. Again, same thing. All right. Try some of these out. See how they go. All right. Pause this thing and follow it along. And I made a mistake here, so don't look at that 3. My circles are for boxes. All right. And that's what we're looking for there. That's not involved. There's that excess again. And whenever you see excess, the other guy is going to 0. this is where I wanted to get into, the limiting reactant. So, and I'm going to use a bit of animation, slideshow. Let's have a look here. Determine the number of molecules that can be made by this given equation here. So I have two of these guys, 2 moles of this produce 1 mole, 2 moles of this plus 1 mole of this produces 1 mole of this. That's what's going on here. 2, 1, 1. So that thing is just moving along. Uh-oh. So what's going on here is this one here is in excess. This is what I meant by excess. We have too much of it. Here we didn't have enough of this guy here. So this one here we call the limiting reactant. We ran out of it. And what happened to the reaction? It stopped. Okay? The limiting reactant is the reactant that limits the amount of product that can be made. Okay? And I'm just going to jump here. Okay? There is always leftover excess reactant. Okay? And this is a silly little slide. I think it kind of confuses things more. Like I don't really, we got 8 wheels and 4 frames and 3 pedals, and so I can make 3 bikes, but then here what did I run out of? I ran out of pedals. So in this case here, my pedals would be my limiting reagent. All right. The one thing I want you to notice is I'm going to scroll back. You see I'm scrolling back all to these guys here that we were just doing. Now, it doesn't matter if we were doing mole or grams to mole or molecules to mole or whatever it was. I gave you the chemical reaction. You have the molar ratios. I'm asking for one thing, and I only give you one thing. See here? Let's pick another one here that's kind of easier to see here. Okay, there's your molar ratio. I'm asking for this one right here. I give you one thing. So bang, 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 there's your box, away you go. So I asking for one thing, and I've only given you one thing. If you see that I have given you 2 things, that is now ding, 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 limiting reagent. It's a little different. So go back, all the ones we've been doing there for the past 20-25 minutes. Okay? I've asked for 1 bit of information, and I've only given you 1 bit of information, and that'll give you 3 out of the 4, so you can do a box. Yeah, I might give you grams, so you might have to flip it into moles, or I might ask for molecules. At the end, you might have to flip it into molecules, but really there's only 1 box, because I've only given you 1 bit of information, and you use 2 bits of information from the molar ratio. Let's have a look here. Calculate the number of moles of water that can be made by the reaction of 2 moles of hydrogen and 1 mole of oxygen. You see how it's different here? I've given you 2 bits of information, and I'm asking for the number of moles of water. Okay, so if you see that I'm asking for something and I give you 2 bits of information, woohoo! Whoa, this is different from above. Okay, so here's your chemical reaction. All right. You're going to do the exact same thing. You're going to do your molar ratios, 2, 1, 2. Same thing. In this case, though, these are the numbers I've given you. So, I've given you 2 moles of this. I've given you 1 mole of this. And I'm asking how many moles of this I can make. Well, in this particular experiment, the molar ratios are 2, 1, 2, and I've given you 2, 1. So basically, this reactant and this reactant will go to 0 at the same time. All right? Because this tells me so. And this is what I mean, man. This molar ratio is everything. I can't even do these without these numbers. Okay? And these numbers tell me that I have to have 2 of these, I have to have 1 of these, and these guys here will stop. They will run out at the same time to make 2 of these guys. Well, the question here is asking how much of this. Well, judging by the numbers are exactly the same, the answer is going to be 2 moles. And both reactants will go to 0 at the same time. Let's have a look here. Same equation, all right? But I'm looking to calculate the number of moles of water that can be made by the reaction of 1 mole of hydrogen gas and 1 mole of oxygen gas. So, what am I looking for? Calculate the number of moles of water. Okay, X moles. How many moles of oxygen did I give you? 1. How many moles of hydrogen did I give you? Only 1. Well, this one here, easy enough, you might be able to see it, that I have to have 2 moles of this to react with only 1 mole of this. 2 moles reacts with 1 mole, makes 2 moles. Well, what if I only have 1 mole of this and I still have 1? This one here, I need 2 in order for this one to go to 0. This one here, 2, I need 1 of these guys for it to go to 0. So what's going to go on here? I only have half as much. So which one is going to run out first? All right. And hopefully you can see there that this one here we're going to run out of first, because if this is going to go to 0, I have to have 2 of these. Well, I don't. All right. I only have 1 of these. Can you tell me how much of this we are going to use? How much? If this is going to go to 0, how much of this am I going to use? Well, look at your ratio here. 2 to 1. So what's 2 to 1 of this? It means I'm only going to use 0.05 of this, and 0.05 of this is going to be left over. So how much of this am I going to make, I guess? This one here we're going to run out of, so then the reaction is going to stop when this 1 mole goes to 0. Well, look at this. 2 makes 2. 1 will make 1. And I'll show you how to set these up. These ones here aren't so bad. You can actually kind of visualize these. Some of them not so easy to visualize. And this is how I do it. Using the same example here. All right, exactly the same. I break it up into scenario 1 and scenario 2. And what this means is here are my theoretical. This is my molar ratio. Okay, that's your go-to. It's always there. These are my experimental. This is what I'm giving you in the question. All right, and then there is what I'm asking for. All right, but the experimental, this is what you're going to set up with. So this is real. This is what I've given you to play with. All right, so scenario 1, I put this guy here. This is the experimental. This is actually what I gave you. And what this means is, if this is going to go to 0, because one of them is going to go to 0, which one is going to go to 0? So this is your experimental, and then there's scenario 2. And this number goes there. And what we're going to do is we're going to set up a 2 scenario system, and we're going to find out which one is going to go to 0 and which one is not going to go to 0. And how we're going to do that is we're going to find out which one is a false statement. So remember our boxes? So when you get into the limiting reactant, you're going to do 3 boxes. 3 of them. So have a look here. If this one here, and you see these guys here, they don't exist right now. Let's just cancel them. They don't exist. All right? And this is what you're going to set up right here. Scenario 1, Scenario 2, you're going to draw this out, the whole thing. You're going to put your information, bang, this information is going to go here. So what you're going to do is you're going to set up a box. If this is going to go to 0, how much of this do I theoretically need? So right here, those 3 are your box. This one here is your X. You're going to crisscross, and here you get 0.5 mole. This is theoretical. By the way, do I actually have 0.5 mole of this? Well, actually I do. So this statement here is theoretically possible. But let's go and do the other one just to find out. If this one here is going to go to 0, how much of this one do I need? And you see how they're underneath each other? So now you're going to do box, 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 X. And if you set it all up, you're going to get 2.0 mole. Do I have 2.0 mole of this guy here? No, because these guys are theoretical. These are real. And if this is going to go to 0, if 1 mole of this is going to go to 0, I got to have 2 moles of this. There's no other way around it. Do I have 2 moles of that? No, I do not. So this whole thing here is a false statement. It's a false. You ignore it, cancel it, scratch it out. This is your real statement right here. This is what you're going to use to find out your answer. Now, calculate, we've already done 2 boxes. We're going to have to do 3 boxes. Calculate the number of moles of water. So you would choose this one, this one, this one, and here's your X. And you will find out there that the answer will be 1 mole. You could actually even do this one, this one, this one, find your X there, and you'll get the same answer. All right. Let me just reverse all this here. There we go. Let's have a look here. And this is the answer to this guy here. Okay, and what I've done is it's the exact same question as slide 44. What we've got here now is you set it all up. There's your molar ratio. Okay, what's the information I gave you? This is real. Scenario 1, Scenario 2. You do box number 1. All right. You find this answer. Then you do box number 2. You find this answer. Which one is valid? Which one is not valid? Cancel the bogus. And then you do box number 3 and you get the answer. Let's have a look here. Calculate the number of moles of water that can be made by the reaction of 3.4 moles of hydrogen and 1.75 moles of oxygen. Whoa. Can't tell this. Can't even look. I have no idea what's going on. So they're looking for the number of moles here. But they've given us this and they've given us this. It's not easy to visually tell. We must do a calculation. So let's set this all up. Again, you're going to set it up the same way as before. Scenario 1, Scenario 2. Okay? So under here, you're going to have Scenario 1, Scenario 2. This is going to be your real for hydrogen. This one here is going to be your real for oxygen. Of course, you're going to have this here. All right? So now hopefully this kind of makes sense. All right. So here's your real for hydrogen. Here's your real for oxygen. Now you're going to do box number 1 to find this experimental value. And in this case here, I found a number of 1.7 moles. Do I have 1.7? No, I have, oh sorry, I do. All right, I have 1.75. All right, so this one here may be possible. Now this is my real, and you can write real and real, experimental, experimental, just to keep them straight. So here I have 1.75 moles of this guy, which is what I gave you, here and here. There's your box, and you'll do another box, and you'll find there that experimentally, if this is going to go to 0, I need 3.5 moles of this. Do I actually have 3.5 moles? No, I only have 3.4 moles. So that means that this one here is bogus. Okay, we've done 2 boxes. This one here is bogus. This is the one we are going to move forward with. Okay, and the answer is looking for the number of moles of hydrogen. Okay, based on using this amount. You could use this box, get the answer, or you could use this one, you'll get the same answer. Okay, and that's how we do this. And the answer I think we found is 3.5 moles. Okay, what do we got here? And again, the same question, just different numbers. And which is a limiting reactant with 3 moles of copper are reacted with 3 moles of silver nitrate. Here I'm just asking for which one is going to go to 0 first. Set up your scenario 1, scenario 2, real, do a box, find an experimental. Okay, do another box, real, find your experimental. Which one is bogus? Cancel it, go forward with the other one, find your answer. All right, so that is the course, and I know it's new, but I don't want you to be afraid of it. There is no lecture next week. Okay, I'll just post some questions, we'll have some video, we'll do some more questions, there might be a test review with answers, and you have 2 weeks until the final exam. I think you guys are going to do great. Your assignment is absolutely geared to the exam. Absolutely. That's why my assignments are like that, because not only am I trying to instill knowledge, I'm trying to help you guys prepare you to pass the test. Okay, so good luck with that, and be safe out there, and keep your emails coming. Some of you guys are embarrassed about emailing me, oh my goodness, 3 times in a day. It's all good. It's all good. Just be safe, be happy, eat some good food, keep at this, because honestly, you're going to see this the first 7 weeks of next semester Chem. Okay, we take it even further. So practice this out and let me know if you're having issues. Take it easy, guys.